The next point, we should ensure whatever we see is clear.
That means work is being done, we can see that it is in opposite direction.
Hello and welcome to the Kaduna State Ministry of Education e-learning platform. Today in chemistry, your usual chemistry teacher, Mr. Philip Mamman, will be taking on the topic relative atomic mass, molecular mass, empirical formula, molecular formula, and the concept of mole. If you followed our last lesson, we did discuss symbols and formula. Today we'll be relating our last lesson to today's lesson for easy understanding. Under our topic today, we'll be discussing what is the definition of relative atomic mass, molecular mass, mole, empirical formula, and of course, molecular formula. Now, in our previous lesson, we have learned that the atomic mass of an atom is the number of protons plus the number of neutrons in that atoms. And we did also say that there are isotopes, and that is why atomic masses are in fraction or decimal. Now, today we'll be looking at how we can put these atomic masses together, considering the non-isotomic mixtures. And in that regard, we'll be defining relative atomic mass with respect to an element, which is carbon-12. But before then, it was done with respect to hydrogen. You will see now that we say atomic mass of an element, not just the mass measured out by the mass spectrometer. Sometimes elements may occur as different isotopes, which have different atomic masses. The weight average of the different atomic masses of the isotope of a particular element gives the atomic mass of the element. This relative atomic mass is not always a whole number. Now, by that we mean that when there is an isotomic mixture, you find out that the relative atomic mass will be in fraction or decimal. Remember, we don't have half proton or quarter proton or half a neutron or quarter neutron. These values are obtained by calculations, and that is why we use the mass spectrometer to weigh out the masses of these atoms. Now, relative atomic mass, earlier the masses of hydrogen was used to determine the relative atomic mass of an atom, but it has been phased out because of the existence of isotopes. Like I said earlier, previously, the relative atomic mass was measured with respect to hydrogen. But because of isotope and their relative abundance, it was now taken to carbon-12. I said carbon has 3 isotopes. Carbon-14 is radioactive and not stable. But of course, carbon-12 has a relative abundance of about 98.9%, which is the bulk of the carbon in the atmosphere. And carbon-13 has 1.1% abundance. Like I said earlier on, carbon-14 abundance is negligible. If you put together 98.9 and 1.1, you find out we have 0.00 something, which is very, very negligible. And it is unstable because it is radioactive. Remember, in our previous lessons, we say that the radioactivity of an element is determined by the proton to neutron ratio in that atom. Now, relative atomic mass by definition. Like I said, carbon-12 has been adopted by scientists as a standard for defining relative atomic mass. Sometimes if you see AR in your textbook, it refers to as relative atomic mass. Now, all the atomic masses of elements determined based on the hydrogen were adjusted to conform to the standard. And we mean to conform to the standard of carbon-12, which is the now used element for references. Now, relative atomic mass of an element is the number of times one atom of that element is heavy as 1/12 the mass of mass of one atom of carbon-12 isotope. In another word, we say the relative atomic mass of an element is the mass of an atom of an element on a scale where carbon-12 weighs 12 units. So you can see by that reference, we say it's 1/12 the mass of carbon-12 isotope. So that is the definition of relative atomic mass. If you have your periodic tables or your textbooks, you will find out that every atom has a relative atomic mass. And like I said, from hydrogen, which has relative atomic mass of 1.008, now when you approximate the value, you have 1. And that of helium to be 4.002. When you approximate the value, you will have 4. And I'm sure that at SS3, you should be very, very conversant with the atomic mass of at least the first 30 elements. That's from hydrogen to zinc. Now, I'll be giving you that of the first 20 elements, and I will be using it as reference when we'll be taking examples. Remember, I said the reason why they are in fraction or in decimal is because they exist as isotope or in isotopic mixture, and that is in relationship to their relative abundance in the atmosphere. Some isotopes are more than the other in abundance. My wonderful students, if you follow this definition, you find out that there's a relationship between relative atomic mass and relative molecular mass. While that of an atomic mass is for atoms, the molecular mass is for molecules. And in our previous lesson, we have established that atoms or molecules are made up of one or more atoms coming together. So we'll see how we can relate that as we make progress. So we move to the next slide, which is that of relative molecular mass. We say the mass of a molecule of an element or compound are also expressed in terms of the mass of atom of carbon-12 as a standard. And the reason is very, very straight, because these molecules are made up of atoms. So if they are made up of atoms, the same basis can be used to outline the masses of the molecules as a unit. So the relative molecular mass of an element or a compound is the number of times the average mass of a molecule of each is heavier than 1/12 the mass of an atom of carbon-12. In other words, the relative molecular mass of a molecule is the mass of a molecule on a scale where carbon-12 weighs 12 units. Remember, a scale is a unit for measurement. In this case, we say it's a mass spectrometer. Now, you see, I said relative molecular mass can be calculated by summing up the atomic masses, AR. Remember, I say AR stands for atomic mass of all the atoms that makes up 1 mole of the molecule. So if you have a molecule, so you can calculate the relative molecular mass by summing up the masses of the atoms that makes up that molecule. In some textbooks or in some contexts, it's referred to as formula mass. It's referred to as what? Formula mass, because you obtain it from the formula if correctly written, as we'll see shortly. Now, we'll take some very few examples as you're going to see. Calculate the relative molecular mass of carbon-4 oxide. In our last lesson, we taught you how you can write correctly the formula of carbon-4 oxide. So, if you know the formula of carbon-4 oxide correctly, you see that it's CO2. CO2 is the formula of carbon-4 oxide. And the mass of one atom of carbon is 12. While that of oxygen is 16. So relative atomic mass of carbon is 12 and relative atomic mass of oxygen is 16. But remember, I said in carbon-4 oxide there is 1 carbon and there are 2 hydrogens. So to get relative molecular mass of carbon-4 oxide, that's RMM, standing for relative molecular mass, we say it's equals to atomic mass of carbon plus atomic mass of oxygen times 2. Why? Because there are 2 atoms of oxygen in carbon-4 oxide. And as you substitute, for carbon is 12, that's why we say 12 times 1, because there's 1 carbon in carbon-4 oxide, and for oxygen is 16, that's why we say 16 times 2, which gives you 44. Now, we will ask, why is there no unit there? Remember, in science, anything that is relative does not have a unit because it's a comparison or a ratio, and that's why you don't have any unit attached to it. So take note, in an examination, if you are asked to calculate relative molecular mass, there is no unit, because if you put a unit there, you lose the mark for the final answer. Another example is calculate the relative molecular mass of tetraoxosulfate 6 acid. Remember, you must know the formula correctly. And the correct formula of tetraoxosulfate 6 acid is H2SO4. H2SO4. So if you are calculating the relative molecular mass, it will be H times 2 because there are 2 H's in H2SO4, and S times 1 because there is 1 sulfur, and of course O times 4 because there are 4 oxygens. So if you substitute the value, you have 1 times 2 plus 32 times 1 plus 16 times 4. Obviously, it's because the relative atomic mass of hydrogen is 1, relative atomic mass of sulfur is 32, and relative atomic mass of oxygen is 16. That will be arithmetic. When you sum up these values, you get 96. Remember I said there is no unit because it's relative molecular mass. The next example is calculate the molecular mass of aluminium tetraoxosulfate 6. And as you can see, the molecular mass of aluminium tetraoxosulfate 6 is how we have to get the correct formula of aluminium tetraoxosulfate 6. And it is Al2SO4 open bracket close bracket 3. So it means that the 3 outside the bracket is for both sulfur and oxygen, such that the molecular mass of aluminium tetraoxosulfate 6 is aluminium times 2 because aluminium is 2 in the formula, sulfur times 3 because of the 3 outside the bracket, of course oxygen times 12 because 4 times 3 is equals to 12. And that will give you, if you put the arithmetic, you will get 342 grams per mole. Now the unit is appearing because we are not calculating relative molecular mass, but molecular mass. In some parlors, they call it molar mass. So if you hear molar mass, we are talking about the same thing. My wonderful students, we'll be looking at the concept of mole. Oftentimes, students look at mole as a short form of molecule. In chemistry, that's not true. A mole is a unit or a tangible unit of quantifying a quantity or amount in chemistry. Like you use your measure to measure your rice and other things. So you'll be seeing what a mole means. I say the mole is a unit of chemical measurement for counting of chemical quantities instead of measuring chemical particles as individuals. It says the particles are measured in tangible units called mole. So today you know that a mole is a unit, not a molecule. So you can see that 1 mole of a substance is the amount of that substance containing as many elementary particles or entities. When we say entities, we mean things like atoms, molecules, ions, electrons, protons, etc. These are things that we refer to as particles, and there are in 12 grams of carbon-12 isotope. And numerically by value, it has been calculated to be equal to 6.02 times 10 raised to power 23 particles. Now remember, we call it Avogadro's constant or Avogadro's number. So if you see Avogadro's number, you know we are talking about 6.02 times 10 raised to power 23. It's very, very important that you remember it. In some examination, you are not given these constants. So when you remember them, you'll be able to use them accordingly. So to calculate the number of moles, we say mass of a substance all over molecular mass or atomic mass. Now use molecular mass if it's a molecule, but use atomic mass if it's an atom. Take note, there's a difference between atom and molecule. In other words, the number of moles is equals to number of particles over Avogadro's number. You can see how to apply each of these numbers if we move forward. Now I want you to note this particularly, that molar mass or molecular mass is the mass of 1 mole of a molecular substance measured in grams per mole. Remember I said that if it's relative molecular mass, there is no unit. And I say atomic mass is the mass of 1 mole of an atom of a substance. And it's measured in grams or atomic mass unit, AMU. That's the unit for atomic mass. Remember, we have molar volume of gases. Gases exist at STP. They can occupy 1 mole of a gas can occupy a volume equal to 22.4 dm cube. If you convert to centimeter cube, it's equal to 22,400 centimeter cube. These are important terms and very important constants. I hope you remember them. When the time comes, they should be at the tips of your fingers. Let's take example. How many moles are there in 8 grams of oxygen atom? Remember, it's oxygen atom. The mass of the atomic mass of oxygen atom is 16. And that is why in the formula you have mass over atomic mass of oxygen. 8 divided by 16, which gives you 0.5 mole. The second question says 8 grams of oxygen molecule. In a molecule of oxygen, there are 2 atoms, and that is why you have it to be 16 times 2 equals to 32. So mass 8 grams over 32, which is the molecular mass of oxygen, and it will give you 0.25 moles. So that's that on mole concept. Very importantly, there are other examples. Calculate the number of atoms in 20 grams of calcium. Remember, I said it's number of atoms. So number of atoms is the same as number of particles. So first and foremost, you must calculate your number of moles, which is number of mole is equals to mass in grams over atomic mass. So the mass is 20, the atomic mass if calcium is 40. So you get your number of moles to be 0.50 moles. Then you substitute in the place of number of moles, and you have your Avogadro's constant, and you make number of atoms subject of the formula. And your final answer will be 3.01 times 10 raised to the power of 23 atoms, as the case might be. As we round up our today's lesson, I'd like us to look at the concept of percentage composition or percentage by mass. It's just the percentage of an atom or water of crystallization in a molecule. Sometimes, like I said, percentage composition of an element is the total mass of that element over relative molecular mass of the compound times 100 over 1. In some parlors, you'll be asked to calculate percentage of water of crystallization, which is the total mass of water of crystallization all over relative molecular mass of a hydrated compound times 100 over 1. In my last class, I told you that hydrated compound is a compound that contains water of crystallization. Now let's take example on this. So say calculate the percentage composition of oxygen in aluminium tetraoxosulfate 6. Now earlier we have calculated the molecular mass of aluminium tetraoxosulfate 6 and we got 342 grams per mole. So the formula for percentage composition says total mass of the element, in this case oxygen. If you look at the formula, you find out that we have 12 oxygen in aluminium tetraoxosulfate 6. And that's why we said oxygen times 4 times 3, 16 times 4 times 3. You can summarize it as 16 times 12, and you will get 192. And that will become your total mass of element all over at molecular mass of compound times 100 over 1. The next one says calculate the percentage by mass of water of crystallization in copper 2 tetraoxosulfate 6 pentahydrate. Pentahydrate there means that that compound have 5 molecules of water of crystallization. So if you look at the solution, you find out that 5 molecules of water of crystallization is the total mass will be 5 times 1 times 2 plus 16. 18 times 5 gives you 90. Now if you look at the molecular mass of copper 2 tetraoxosulfate 6 pentahydrate, because it's an hydrated compound, you have a value of 249.5. So if you substitute 90 over 249.5 times 100 over 1, you will get the percentage to be 36.07%. So that is the example on that. Now we'll take two very important concepts, that's empirical formula and molecular formula. The empirical formula of a compound is the simplest formula of that compound that shows the mole ratio of atoms in the compound. Remember, the important word there is mole ratio of atoms. And to calculate empirical formula, the first thing you have to do is to calculate the number of moles. We have done that earlier, which is mass. And sometimes the mass is replaced by percentage by mass over atomic mass. Then the next thing is to look for the lowest value to get your mole ratio by dividing through by the smallest value of mole. And the last step is writing the mole ratio as subscript corresponding to the atoms. All right, so as we look at an example here, I will say, what is the empirical formula of the oxide of lead, in which 10.3 grams of lead combined with 1.6 grams of oxygen? 10.35 grams is the mass of lead, and 1.6 grams is the mass of oxygen. So you find your number of mole 10.3 over 207, which is the atomic mass of lead. And of course, it will give you 0.05 moles. Then 1.6, which is the mass of oxygen, over 16, which is the atomic mass of oxygen, will give you 0.1 mole. Now, to find the ratio, mole ratio, between 0.05 and 0.1, which one is the lowest? Of course, it's 0.05. So you divide all through with this. 0.05 over 0.05 and 0.1 over 0.05. So that is 1 is to ratio 2. And like I said, you write a subscript such that lead will be 1 from here and oxygen will be 2 to give you lead 2 oxide. That's the formula of lead 2 oxide. So I would like to stop here. My noble colleague, Malo Ibrahim Umar, will come and talk about molecular formula, give you an assignment, and we'll meet in another class, as I'm sure you will follow what I have said. And as your exams are fast approaching, they'll be very, very useful during your exam. I remain your teacher, Mr. Philip Mamman. Have a wonderful day. Stay safe, keep reading, and remain blessed. Thank you.
Good day, my wonderful students. My name is Ibrahim Umar. I'm here to build on the wonderful presentation presented by Mr. Philip Mamman, and I will start with molecular formula. Molecular formula is the actual formula of a compound that shows the exact number of atoms in a compound. Unlike the empirical formula that shows the ratio, the molecular formula shows the actual number of elements, and it is represented as the formula of that compound. How do you calculate the molecular formula? The first thing you do is you have to get your empirical formula first. Then from the empirical formula, use the formula that says step 1. Use the formula. Molecular formula is equals to empirical formula times n. That means you need to calculate n first. Now step 2. Use the relationship that says molar mass of empirical formula times n equals to molar mass of the compound. That is, find n from there to be what? N equals to molecular formula of the compound all over the molecular formula of the empirical formula. Then when n is found, substitute it. That is, you apply it in the formula that molecular formula is equals to empirical formula times n, and then you get the actual formula of the compound. I will support that with an example. Example, it says a hydrocarbon contains 92.3% of carbon and 7.7% of hydrogen. Now calculate 1, empirical formula, 2, molecular formula, given that the molar mass of the compound is 26 grams per mole. So Mr. Philip teach you how to calculate empirical formula, but I'll take it over again. Now, to calculate the empirical formula, what is the percentage by mass of carbon? It was given as 92.3. Percentage by mass of oxygen, it was given as 7.7. Now you find the number of moles by dividing by the relative atomic masses. Now, under carbon, you have 92.3 divided by 12. Then you end up having 7.7. Then under hydrogen, you have 7.7 divided by 1, which is the same thing as 7.7. Here, the numbers are the same. So there is no one that is the least. So you can divide it by any one. And then to find the mole ratio, you said 7.7 divided by 7.7, you obtain 1 under carbon. Also, 7.7 divided by 7.7, you also obtain 1 under hydrogen. That is, the ratio is 1:1. The empirical formula now is given as 1 carbon to 1 hydrogen. That is CH. So now, step 2, to calculate the molecular formula. You said molecular formula is equals to molar mass of empirical formula times n, which is equals to molar mass. And the molar mass was given from the equation to be 26. That is, the empirical formula is CH. That is, CH multiplying n is equals to 26. Now, the mass of carbon is 12 plus mass of hydrogen, which is 1. 12 plus 1 multiplying n is equals to 26. 12 plus 1 is 13. That is, 13n is equals to 26. Now, to find n, you divide both sides by the coefficient of n, which is 13. So we have n is equals to 26 divided by 13, and you obtain 2. Now, going to step 3, to obtain the actual molecular formula, you multiply the empirical formula by 2. That is CH, which is the empirical formula, times 2. That is 2 carbon and 2 hydrogen. This is the empirical molecular formula. My students, the molecular formula was found to be C2H2. So that brings us to the end of the lesson, and I will support, or I will find out how good you assimilate the subtopic by giving you the following assignment. Question 1. Define the following terms. A. Relative atomic mass, RAM. 2. Empirical formula. C. Molecular formula. D. Mole. Question 2. Differentiate between the following. A. Empirical formula and molecular formula. 2. Mole and molecule. Question 3. On analysis of an organic compound, it was found to contain 2.00 grams of carbon, 0.34 grams of hydrogen, and 2.67 grams of oxygen. Calculate the following. I'll take it over again. On analysis, carbon was said to contain 2.00 grams, hydrogen contains 0.34 grams, and oxygen contains 2.67 grams. So now we are expected to calculate empirical formula. You also calculate molecular formula if the molar mass is 60 grams per mole, and finally deduce the molecular structure of the compound and hence give the IUPAC nomenclature. My students, I hope you enjoyed the lesson, but I'll give you the reference. You can contact STAN Chemistry Textbook for SS1 by STAN, that is Science Teachers Association, or of course you can contact Ababio, that is New School Chemistry, and we have Understanding Chemistry by Godwin O. Ojokuku. If you solve your questions and you want to give us, or you need feedback or further questions, you can contact Mr. Philip Mamman on his number 080-2659-8861 or Ibrahim Omar 070-3620-2842, or you can contact Mr. Philip O. Williams Ishaku on 081-606-70920. Have a wonderful day, my students. Remain safe, remain home, and keep learning. Thank you.